Auroras. A cosmic light show. Aurora is the name given to the glow or light produced when electrons from space flow down Earth's magnetic field and collide with atoms and molecules of the upper atmosphere in a ring or oval, centered on the magnetic pole of Earth. The collisions create light similarly to electrons in neon lights, where they collide with neon and other gases to produce different colors. The aurora is also called the northern lights in the northern hemisphere and southern lights in the southern hemisphere. The technical term for the northern lights is aurora borealis and the southern lights are called the aurora australis. The word borealis comes from the Latin word boreal, which means northern or from the north. The word australis is Latin for austral, which means southern. The word aurora is derived from the name of the Roman goddess of the dawn, Aurora, Greek, Eos, who traveled from east to west announcing the coming of the sun. Goddess Aurora is a figure of Greek mythology who symbolizes the dawn and the start of a new day. Her Latin name, Aurora, literally translates to dawn, making her an ideal figure to stand for the morning. She was the daughter of the Titans Hyperion and Thea, and her siblings included Helios, the sun god, and Selene, the moon goddess. Auroras by appearance. Diffuse auroras. Faint and featureless glow, seen as a widespread light across the sky, often occurs before a substorm or in the outer edges of the auroral oval, hard to see with the naked eye. Discrete auroras. Brighter and structured forms like arcs, rays, or curtains, occur during more intense geomagnetic activity, can appear as moving or pulsating lights. Auroras by shape. Arcs. Smooth, elongated bands of light across the sky, often appear before more active auroras, can stretch from horizon to horizon. Curtains or drapes. Appear as rippled sheets, like fabric in the wind, commonly caused by field-aligned currents and particle acceleration. Coronas. Radiate from a central point directly overhead, caused by perspective effect when looking straight up into the aurora. Rays. Vertical stripes or columns of light, extend upward from the auroral arcs, caused by electrons following Earth's magnetic field lines. Pulsating auroras. Appear as patches that blink on and off, pulsate at regular intervals, typically occur after midnight and are more common during the declining phase of a substorm. Colors. The images below shows different colors of aurora. The left panel shows a red aurora. The middle panel shows the most common green aurora. The right panel shows green aurora with purple lower edges. Note that modern digital cameras are often more sensitive than the human eye and can detect aurora and the colors of the aurora when it is too dim for humans to see it. One particular aurora color is the result of excited nitrogen being further excited by photons from the sun or sunlight. This sunlit aurora typically occurs near sunrise or sunset and can be seen as a purplish color at the top of the auroral rays as seen in the figure below. The color of an aurora depends on which gas is excited by the incoming particles and where that gas is located in the atmosphere. When a particle interacts with either oxygen or nitrogen, the excess energy from the interaction results in a burst of light. Electrons hit air molecules. Molecules are excited. Molecules give off light as they calm down. Altitude, gas composition, primary light color. Above 120 miles, oxygen, red. 75 to 110 miles, oxygen, green. 75 to 110 miles, nitrogen, blue. Below 60 miles, nitrogen, pink. Oxygen and nitrogen can emit green, red, or blue lights. The combination of the different amounts of gases can produce purple, pink, and white lights. Altogether, the cascade of energy, location, and interactions produce the wonderful colors of the auroras. Oxygen atoms glow green, the color most often seen because nitrogen atoms are harder to energize than the oxygen atoms. The video shows what active aurora looks like in real time. This video is unique in that it is not a time-lapse but is showing the true nature and motions of the aurora. It also shows the true colors of the aurora and their spatial and temporal relationship to each other. It is possible to distinguish the prompt purple nitrogen emission along the lower edge of the aurora from the longer-lived green atomic oxygen emission higher up in the atmosphere. Geomagnetic activity scales. The planetary K-index, KP index, is a global measure of geomagnetic activity in Earth's magnetic field caused by solar activity, especially solar wind and coronal mass ejections, CMEs. It is a quasi-logarithmic scale from 0 to 9, where higher numbers indicate stronger disturbances. The NOAA Space Weather Scales, the Geomagnetic Storm, or G-scale, is used to describe space weather that can disrupt systems on Earth. The auroras form in an oval around the Earth's poles in an area called the auroral zones. Auroral zone is a ring-shaped region around the magnetic poles where auroras are most likely to be observed. Typically centered around the magnetic poles. Areas in the northern auroral zone include North Norway, Sweden, Finland, Iceland, Greenland, and Canada, the North of American state Alaska, and northern Siberia, in Russia. Southern auroral zone includes Antarctica, south of New Zealand and southernmost part of Australia. Aurora oval occurs during normal solar activity. Suboraural oval zone occurs during strong solar activity. Solar storm zone occurs during extreme solar or geomagnetic storms. Auroral zones in northern hemisphere. How far south can aurora be observed? Auroral zones in southern hemisphere. How far north can aurora be observed? A vivid aurora streams over the Earth as the International Space Station orbited 273 miles above the southern Indian Ocean in between Australia and Antarctica. The Aurora Australis arcs above a partly cloudy Indian Ocean in this photograph from the International Space Station as it orbited 269 miles above in between Australia and Antarctica on June 12, 2025. From space, the aurora is a crown of light that circles each of Earth's poles. The image satellite captured this view of the Aurora Australis, Southern Lights, on September 11, 2005, for days after a record-setting solar flare sent plasma flying towards the Earth. The ring of light that the solar storm generated over Antarctica glows green in the ultraviolet part of the spectrum, shown in this image. The image observations of the aurora are overlaid onto NASA's satellite-based blue marble image. From the Earth's surface, the ring would appear as a curtain of light shimmering across the night sky. The ACE satellite refers to the Advanced Composition Explorer, a NASA spacecraft launched to study particles from the Sun, the interstellar medium, and other cosmic sources. The auroral oval extends into the dayside part of Earth, but you cannot see the aurora during the day. As the auroral activity picks up, the auroral oval expands equatorward. Earth isn't the only planet that experiences auroras. Any planet with an atmosphere and a magnetic field is likely to have auroras. Spectacular auroras have been observed on Jupiter and Saturn by the Hubble Space Telescope. The aurora is formed from the interactions between the solar wind streaming out from the Sun and Earth's protective magnetic field, or magnetosphere. The aurora is one manifestation of geomagnetic activity or geomagnetic storms. As the solar wind increases in speed and the interplanetary magnetic field, IMF, embedded in the solar wind turns southward, the geomagnetic activity will increase and the aurora will become brighter, more active, and move further from the poles. Even moderate solar wind creates aurora, so there is usually a weak aurora somewhere even when there isn't a big geomagnetic storm. Electrons accelerated from the bow of the magnetosphere. Electrons accelerated from the tail of the magnetosphere. There are two types of solar events that create big geomagnetic storms that are associated with bright and active aurora. The first is a coronal mass ejection, or CME, which can be described as 1 billion tons of plasma ejected from the Sun, traveling at 1,000,000 miles per hour. When a CME arrives at Earth, it can produce some of the biggest geomagnetic storms and thus, some of the brightest and most active auroras that extend furthest toward the equator. The second solar event that can create moderate-sized geomagnetic storms is called a coronal hole. Coronal holes are regions on the Sun's surface that appear darker, cooler, and less dense than the surrounding areas. These holes are areas where the Sun's magnetic field lines open out into space rather than looping back into the Sun. This allows solar wind, a stream of charged particles, to escape more freely. Coronal holes are the source of high-speed solar wind streams. When these high-speed streams arrive at Earth, they can produce active auroras. But the geomagnetic storms and aurora associated with coronal holes is less active than those from the biggest and fastest CMEs. Sources of solar wind. Coronal mass ejection, CME, with or without solar flare. High solar winds, strong solar storms. Coronal hole wind stream. No explosion, moderate to high solar winds, can lead to moderate solar storm. Solar prominence, filament. High solar winds, strong solar storms. Sunspot regions. Solar flares and coronal mass ejections can take place. Auroras are breathtaking displays of light in the sky, often seen near the Earth's poles. They are a natural interaction between the Sun and Earth's atmosphere. Our Sun generates a strong solar wind, which carries about 1 million tons of extremely hot plasma, electrons, protons, and other particles, away from the Sun every second. Earth's magnetosphere acts like a shield that protects us from most of this constant solar wind, deflecting it around Earth. During a solar storm, such as a solar flare or coronal mass ejection, CME, a large amount of plasma hurls through space at high speeds as part of the solar wind. When this extra solar energy collides with Earth's magnetosphere, some of the electrically charged particles move down strong magnetic field lines at the north and south poles and become trapped in Earth's atmosphere. These particles bounce from the North Pole to the South Pole and back again, transferring energy to molecules in Earth's atmosphere as they go. The colorful, glowing lights of the aurora result when these energized molecules release their extra energy.